Good afternoon. Welcome to the week 3 tutorial of the subject Introductory Organic Chemistry 1 conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Deshaputri from ISER Pune. I am your PMRF teaching assistant for this course, Deepika, and I am doing PhD in chemistry at IIT Bombay. So today in this tutorial of week 3, we are going to discuss and solve a few interesting questions on the topics stereochemistry in organic compounds. Please feel free to ask any doubts or queries related to the questions that we are going to discuss in today's session. So let us start with the first question of this tutorial. Which of the following terms best describes the pair of compounds shown? Enantiomers, diastereomers, or the same compound? So we are given a set of compounds. These are basically disubstituted cyclohexane molecules. So you have to identify and term the pair of compounds as enantiomers or diastereomers or the same compound. These two compounds, the given compounds will be enantiomers if they have a relation of non-superimposable mirror images. And these will be the same compound if the substituents are placed at the same positions of the cyclohexane ring, also oriented in the same orientation in 3D as well. So then they will be termed as the same compound. And they will be called as diastereomers if the two compounds are not mirror images. They do not possess a relation of being mirror images. So how do we identify the pair of compounds as enantiomers, diastereomers, or the same compound? For that, we will have to first identify the presence of chiral or stereogenic centers in the rings present, and then we will assign the stereochemistry in the stereogenic centers present. Okay, so let us move to the first compound present. We have one methyl substituent and one hydroxy substituent present in adjacent carbon atoms of this cyclohexane ring. Let us assign the stereochemistry of these two stereogenic centers. Okay, for that we will have to give priority to the substituents present at this chiral center, and then we will move from higher priority to the lowest priority according to the RS nomenclature rules. So if we have to assign RS configuration to the stereogenic center, what will be the highest priority group for this? It will be this one. Okay, this substituent present in this chiral center will be of highest priority. Then the second priority group will be this one, isn't it? Because if we talk about this group has CH, then OH, and further it has CH2, CH2. And for the second priority group, this group has CH2, two hydrogens are here, CH2, then further CH2 it has. So this will be the first priority group, this will be the second priority group, and this methyl, which is above the plane of the paper, this methyl will be of third priority. We have one more hydrogen here, and since this carbon atom has tetrahedral geometry, that hydrogen present in the center will be below the plane. Okay, you have to imagine this carbon center as a tetrahedral center where these two substituents are placed on the plane of paper, and this methyl substituent is above the plane towards you, and one hydrogen atom is present which will go back to the back side, that is below the plane of the paper, and that will be the fourth priority group. So we have assigned the four substituents present in this carbon center as 1, 2, 3, and the fourth substituent will be below the plane, hydrogen, 4. So if we move from 1, 2 to 3 to 4, 1, 2, 3, 4, and fourth is below the plane, we are moving 1, 2, 3, 4, that is in a clockwise direction. So according to the RS nomenclature rules, if we move in a clockwise direction where the fourth priority group is below the plane, the center will be called as R. Okay. So this center is R. We have assigned the configuration now. Then let us move to the second stereogenic center present in this molecule. Remember, this has been assigned as R, and for the second stereogenic center, that is chiral center present in the first molecule, now we will assign the priority. Okay. So it has four substituents just like the first one. It has one hydroxyl group, two alkyl chains in different directions, and it will have a hydrogen which according to tetrahedral geometry will be projected above the plane, that is to our side. It will come out of the plane and above. So if we now start numbering, that is giving priority to the substituents present in this chiral center, this will be our first priority because oxygen has more higher atomic number than carbon and hydrogen, so it will be the first priority group. So this will be 1, and in between these two alkyl chains, this will be of higher priority because if we move in this direction, it will be this carbon center is connected to 2 carbons and 1 hydrogen, and in this way, in this side, this carbon is connected to only 1 carbon and 2 hydrogens. So if we have 2 carbons in one side and we have only 1 carbon in one side and rest are hydrogens, then this group will definitely get higher priority if we are talking about this center. So this will be our first priority group. This will be our second priority group, and this will be the third priority group. And the hydrogen which is coming out of the plane towards us above the plane, that will be of fourth priority. So let us recall the rules of RS nomenclature. If we are moving from 1 to 4 in a clockwise direction, in an anti-clockwise direction, because 1, 2, 3 anti-clockwise direction, but the fourth priority group is above the plane, unlike not below the plane like the first case, then we will have to reverse the configuration. That is, it will be, although it is anti-clockwise, we will name it as R configuration. Okay. So now we have assigned stereochemistry to both the stereogenic centers in the first molecule, R and R. R, R. So now you have to assign the stereochemistry to the stereogenic centers present in the second molecule, just like we did in the first molecule case. Okay. Okay. So in the first molecule, we have already assigned the stereochemistry R and R. Let us do it in the same way for the second molecule. Okay. For this one, I will not explain in details because we have already done it in the same way for the first molecule. So for this molecule, let us come to this center first. Okay. What will be the first priority group for this one? We have two alkyl chain in two directions and then one methyl and one hydrogen will be there below the plane. That is far from us. So this group will be 1 in a similar way what we did for the first molecule. This group will be 1 and then this alkyl chain will be of second priority. This methyl group will be of third priority and the hydrogen molecule or hydrogen atom with what is coming below the plane will be of fourth priority. So if we move now from 1, 2 to 3, 1, 2, 3. We are moving in a anti-clockwise direction. So we have a case where we are moving in an anti-clockwise direction and the fourth priority group is below the plane. Then we will assign the stereogenic center as S configuration. For the second stereogenic center present, we have this group as the first priority. This alkyl chain is the second priority because I have already told for the first case that we have two carbons for this alkyl chain in this direction. But here we have only one carbon here and then it is connected to two hydrogen atoms. So between these two alkyl chains, this chain will get higher priority as compared to this one. Okay. So this will be of first priority. This will be of second priority and this one will be of third priority. And the fourth one, where is the fourth one? Fourth priority group, which is the hydrogen that is going that is coming above the plane towards us. So we have a case now where we are moving in a clockwise direction. In this way, 1, 2, 3, we are going in a clockwise direction where the fourth priority group is above the plane. Thus, according to RS nomenclature rules, we have a S configuration in this stereogenic center. So now we have all the stereogenic centers assigned configuration of the stereochemistry. So the first molecule has RR configuration for the stereogenic centers and the second molecule has SS configuration for the stereogenic centers. And when we have a pair of molecules having RR versus SS configuration, then they will possess a mirror image relation with and the mirror images will be non-superimposable. Okay. So these two molecules are non-superimposable mirror images having RR and SS configuration and they will be called as enantiomers. Okay. I hope it is clear. So when you are given a pair of molecules having one or more stereogenic centers, first you have to assign the configurations to all the stereogenic centers present. Then you have to compare and suppose we had found out that this was RR and this was RS. Then have been diastereomers because they will not be mirror images of each other. So since we have RR and SS configuration, they will be mirror images and they will be non-superimposable mirror images. So they will be called as enantiomers. I hope it is clear to everyone. So let us move to the next question of this session then. The compound in R configuration is, you have been given 4 molecules and you have to assign the stereochemistry to this chiral compounds. These compounds given in the options do not possess any stereogenic center, but they show axial chirality. Okay, along this axis, they show axial chirality. These axes. So now, this kind of when it comes to assigning stereochemistry to these kind of compounds, like for example biphenyl rings, heteroisomerism we find, and when we have to assign the stereochemistry of these axial chirality possessing compounds, we have to know how to visualize these compounds in a way. Okay, let us try to do that. If we talk about the option A, suppose we are placing our eye in this way, in this direction. Okay, in this place we are placing our eye. Then this hydrogen will be coming out of the plane and the methyl will be going below the plane. And between these two substituents, if we try to assign priority according to atomic numbers or atomic mass, just following the rules of priority in RS nomenclature, we will have to assign this methyl as 1 and this hydrogen as 2. So for this plane, we have assigned the priority as 1 and 2. 1 will be, if we are placing our eye here, 1 will be towards the right side and hydrogen will be towards the left side. So if you look at this plane, we have assigned 1, that is methyl, and 2, that is hydrogen. This plane is sorted. Now let us move to this plane, the vertical plane. Okay, vertical plane of our eye, which will be perpendicular to our eye. Remember, here we kept our eye. So if we look at the vertical plane, we have two substituents now, ethyl and hydrogen. Look at here, ethyl and hydrogen. And of these two, one will be above and one will be below. Okay, one will be above and one will be below in the vertical plane. So between these two, following the atomic number rule, this will be given higher priority and this will be given lower priority. So horizontal plane we have already placed. In the vertical plane, this third priority group will come here and fourth priority group will go below in the vertical plane. Always remember, 1 and 2 priority groups will come first and they will be in the horizontal plane, which are nearer to your eyes. So 1 and 2 we have already placed in the vertical plane. Between these two, third and fourth now we have placed. And now we will move in a direction. Okay, from 1, 2, 3 and so on. So let's move 1, 2, 3. 1, 2, 3. So you can see that we are moving in a clockwise direction. Okay. So we have this molecule as R configuration. 1, 2 and 3. If we come to option B, let us see. First, let's keep our eye here and then give priority 1, 2. See, this first priority group, which is methyl, is away from us. That is, it is going below the plane. Then it will come to the right side of our eye. And the hydrogen, which is coming above the plane, will be left side of your eye. Okay, just imagine the horizontal plane of your eye. 1 will be on the right side and 2 will be on the left side. So let us place the priority numbers in the horizontal plane, 1 and 2. And then let's go back, place our eye and look at the vertical plane now. We have two methyl groups in the vertical planes, in the vertical plane this time. So since both these substituents are the same substituent, then we cannot call this compound as chiral. To be chiral, this compound must have two and two different substituents present. Okay, it must contain two different substituents in each of the planes. Although in the horizontal plane we have two different substituents here, in the vertical plane we are seeing that we have the same substituent twice. So we cannot assign a stereochemistry to this achiral center. Okay, see, we have 1, 2, but 3 and 3. So this compound is not chiral. Similarly, let us go to compound number C now. We will place our eye here, just like the earlier two cases. And then we will try to visualize the horizontal plane first. Okay, always remember horizontal plane first, which plane is nearer to our eye. Okay, so in this horizontal plane, the nearer center is containing two methyl substituents, that is two similar substituents. Again, this center is containing. So in the horizontal plane itself we have the same compound twice. So this compound cannot be chiral. In option D, we have this compound which is possessing axial chirality, and let us place our eye here and we will visualize what is in the at the right side and what is at the left side of our eye in the horizontal plane. We have one methyl and hydrogen. So this will be of first priority and this will be of second priority. First priority will go towards the right and second priority will go towards the left. So you can place the numbers in the horizontal plane. 1, 2. Done. Let's go back, place our eye and look at the vertical plane. We have in the vertical plane one hydrogen and one ethyl substituent. Hydrogen will be above, ethyl will be below. So the third priority will be below and hydrogen will be above. So let us go back to our drawing where we have placed 1 and 2. So 1 is here, 2 is here. Third ethyl substituent is towards the below side of the vertical plane, and fourth priority substituent hydrogen is at the above side. So now let's move from 1 to 4. 1, 2, 3. 1, 2, 3. Sorry, in this way. You have to move in this way. 1, 2, 3. 1, 2, 3. In anti-clockwise direction we are moving. Okay. 1, 2, 3. So since we are moving in an anti-clockwise direction, this will be of S configuration. So we got that among the options given, compound B and compound C were containing the same substituents in one of the planes. So these two are achiral molecules. Compound A, option A, was having R configuration and compound D was having S configuration. So the answer to this question will be option A. I hope this question is clear. Okay, so let us move to the question number 3 now. We have discussed already question 1 and 2. So question number 3, you are given how many stereoisomers are there for the following structure. You are given the structure of this tartaric acid molecule and you have been asked what is the number of stereoisomers present for the given structure. To calculate the number of stereoisomers possible, you have to first identify the number of asymmetric carbons or chiral compounds or stereogenic centers present in the given structure. So let us look at the structure. We have this center and this center as chiral, because if you look at these two centers are connected to 4 different substituents. So these two are the chiral centers present in this tartaric acid molecule. So you following the video lectures, you must know that the number of stereoisomers possible for a structure is calculated as 2 to the power n, where n will be the number of stereogenic centers present in the molecule. So if we calculate for this tartaric acid molecule, it will be 2 to the power 2, because we have 2 stereogenic centers, so it should be 4. This structure should have 4 stereoisomers possible. But if you write down the stereoisomers, you will find that for this structure, one stereoisomer will be this. The second will be of this. So these two are 2 stereoisomers for the given compound, and this is the third one. Okay. The fourth one, which will have the hydroxyl groups placed to the left side of this axis and the hydrogen groups placed to the right side of this axis, that one is also one stereoisomer for the given structure, but the fourth structure and this structure, these two structures will be the same structure. They will be identical according to the rule that they will be superimposable if you rotate one of the molecule by C2 axis, that is 180 degree. Imagine one axis passing through this center perpendicular to this molecule and rotate the molecule by 180 degree. What will happen? The upside COOH group will come downside, the downward COH carboxylic group will go upside, the hydroxyl groups will come towards the left side, and the hydrogen groups will come to the right side. So that molecule and this molecule will be the same one. Okay. So the third and fourth stereoisomers possible for the structure given are the same one. Hence, we will have to count only one of them. Then you will see that only 3 non-identical structures or stereoisomers are possible for the given structure of the tartaric acid molecule. Okay, I hope this is clear that the third and the fourth structure are identical because they are interconvertible by a C2 axis of symmetry, that is by rotation of 180 degree along an axis. So the answer will be C, that is 3 non-identical stereoisomers are present. Let us move to the next question. We have label each asymmetric carbon in the compound below as R or S. You are given this bridged polycyclic molecule where you have a chloro substituent in the bridgehead position and this molecule also possesses a double bond, and you have to first identify all the asymmetric carbons or stereogenic centers present in this molecule, and then we will try to assign R or S configuration to the stereogenic centers present. So as we have already discussed, to be a asymmetric carbon, the carbon center must be connected to 4 different substituents. So this cannot be a stereogenic center or asymmetric carbon. This also cannot be. If we talk about this one, yes, this carbon is connected to 4 different groups. How? In upper side, that is if we move to the above the plane of this bridgehead carbon, this is one substituent, this is the second substituent where you have CH double bond CH and so on, and you have the third substituent along this side, CH2 CH2, and it also contains one hydrogen atom which will be equatorial to this bridged carbon. So thus we have 4 substituents, and let us now give the priority to all the 4 substituents present to this carbon center. So this substituent will be of first priority, just like we discussed earlier, because if we break the structure of this double bond, you will see that this carbon atom is connected to one hydrogen and like 2 carbon atoms. Okay, following the rules of RS nomenclature priority, if you simplify this double bond, you will find that this carbon atom is connected to 2 carbon atoms and 1 hydrogen atom. Whereas if we move to this side, this carbon atom is connected to 1 carbon, this way 1 carbon and 2 hydrogen atoms. So in one side you have 2 carbon atoms and in the other side you have only 1 carbon atom. So this group will get the first priority according to the priority rules. And so between these two, this will be of first priority. Now we have this one will be of second priority. Okay, because between these two we have CH2 here also we have CH2, but if we look at the next substituent, next atom present, like move along this way or versus this way, we have here 1 chlorine atom, but here we have only 2 hydrogen atoms. So following the atomic number rule, between these two we will have higher priority to this above substituent. Okay, so we will have this one as second priority group and this one will be third priority group, and the hydrogen present at the equatorial position will be of fourth priority. So now let us move to 1 to 3. 1, 2, 3. We are moving in a anti-clockwise fashion. So this carbon atom we will have to assign an S configuration. Okay, in this way we are moving. So one asymmetric carbon we have already identified and assigned its configuration as S. Now it's turn for this carbon atom. Okay, because this is also asymmetric carbon and this is also connected to 4 different substituents. This is one, this is the second one, this is third substituent, and the chlorine which is towards us, it is above the plane you can imagine. This will be of the fourth priority. So let's move from, sorry, not fourth priority, the fourth substituent. So thus we have 4 different substituents in this center as well. And now we will assign the priorities and the configuration at last. So this atom will be of first priority because all the other three substituents are possessing carbon atoms, but here we have chlorine atoms. So according to higher atomic number of chlorine, this will be of the first priority. And among the rest 3 alkyl chains, just like we assign priority for the center, this will be of the second priority. Okay, because we had simplified in the earlier case that this carbon is like being connected to one hydrogen and 2 carbon atoms, but these two are connected to only one carbon next and 2 hydrogen atoms placed here. So this will be of second priority, this will be of third priority, because in the second position it is connected to only one hydrogen and 2 carbons, but for this it is connected to only one carbon and 2 hydrogens. So just like in this case, this will be of first priority, this will be of second priority, this will be of third priority, and this CH2 facing one will be of fourth priority. So if we move from 1 to 3, 1, 2, 3, we are moving in an anti-clockwise fashion again. So we have SS configuration for the asymmetric carbons present in this molecule. So we first identified that this molecule given has 2 stereogenic centers present, and those 2 has configuration SS. I hope this is clear. Okay, so let us move to the next question. We have, which of the following structures represent the same stereoisomer? You are given 3 molecules here, A, B, C, and you have to identify which 2 of these 3 molecules are same. Either is it AB are same, or AC are same, or BC are same. You have to identify, or it can be like ABC, all are same. Just they are rotated in an angle and placed in a different fashion, so that you get confused and we think like, oh no, this is not the same stereoisomer. So how do we approach towards solving this question when you are given Sawhorse configurations of Sawhorse conformations of such molecules? First, we will simplify the structures given by converting it to their Fisher projections, because it becomes easier to assign configurations to the stereogenic centers present in the molecules if you convert them into Fisher projections. Okay, and after converting the structures given into the Fisher projections, you can just simply assign the RS configurations to the asymmetric carbons present, and then you will come to know that are the structures given are same or not. Okay, so let's convert the molecule given in option A, or like given as A, to its Fisher projection. For that, we have to bring those substituents to the same direction. Like all the substituents we have to make parallel, which are present on the plane of the paper. We see that this hydrogen at this center and this methyl at this center are placed in the plane of paper. So we will just simply rotate this center by an angle of 180 degree so that this methyl will come to the same direction of this hydrogen, because we need those two substituents which are present on the plane of paper in the same direction. Now you can see that hydrogen and methyl are oriented in the opposite direction. So to bring this methyl to the direction of hydrogen, we will rotate this center as 180 by an angle of 180 degree. And this will not cause any change in the configuration of the stereogenic center, or this will not bring any change to the structure also. Okay, just you have to rotate one center by 180 degree. If we rotate it by 180 degree, this methyl will come parallel to this hydrogen. This chlorine will come parallel to this methyl. Okay, this chlorine will come parallel to this methyl, and this hydrogen will come parallel to this chlorine. I hope you are being able to visualize. This methyl is coming now parallel to this hydrogen. This chlorine is coming parallel to this methyl, and this hydrogen is coming parallel to this chlorine. So we had earlier three planes. Now all the atoms present in each plane are parallel. We just have to lift the molecule now and convert it to Fisher projection. So we had hydrogen here and methyl parallel here. So if we lift it and project it in its Fisher projection, we have methyl and hydrogen. And we have two substituents in each side, like towards right and left. Now we will place them in the Fisher projection. For the center, we have methyl this way and chlorine this way, and this chlorine was parallel to this methyl, so this chlorine and this methyl will be on the same side, and this hydrogen and this chlorine will be on the same side. Okay, so there can be a minor mistake in this Fisher projection, because if you look at the conversion, we have methyl and hydrogen in the axial positions of this chiral axis, and if we place the similar side atoms, we must have chlorine and methyl in one side and chlorine and hydrogen in one side. Yes, so this must be reversed. Okay, to be clear, let us discuss for this structure B given. If we convert it to Fisher projection and we rotate this center by an angle of 180 degree, this methyl and chlorine will come parallel. Okay, this methyl and chlorine will come parallel. Yes, this hydrogen and this methyl will come parallel. Yes, now it is clear. Actually, I was mistakenly saying that this chlorine and methyl will come parallel. No, if we rotate by 180 degree, na, this hydrogen will be later here. So not this chlorine, this hydrogen will be parallel to this methyl. So this hydrogen and methyl will be on the same direction, and this chlorine and this chlorine will be in the same direction if we rotate this center by 180 degree. Now you just have to lift the structure and place it to Fisher projection. You will get hydrogen and methyl in the axial positions and two chlorines on the same direction and hydrogen and methyl in the same direction. Let us try to imagine in this center. Let's rotate it by 180 degree. This methyl will come parallel to this chlorine. If we rotate by 180 degree, this hydrogen will come parallel to this methyl because it will come here above the plane. So this will be above the plane by rotating 180 degree, and this hydrogen and methyl will be in the same direction. Similarly, this hydrogen and this chlorine will be in the same direction after rotating by 180 degree. So B can be written here. Similarly, if we convert C to its Fisher projection, this can be written as this one. So now let us compare the structures. Structure A is having two chlorine atoms in one side and none of the other two structure is having two chlorine atoms on the same side. So we can now exclude the structure A. We are left with these two structures. We can see in this side of this molecule we have chlorine and hydrogen, but in this side of this molecule we have methyl and hydrogen. But I hope you remember for the first question I said if two structures are interconvertible, by rotating one of the structure by 180 degree, that is by rotating it in a C2 axis of symmetry, and they become the same compound, then those two compounds will be called as identical. So for these two structures, let us take one of these. Let us take one. Let us rotate this compound by 180 degree through an axis passing through the red dot, which will be perpendicular to the compound, the plane of the compound, and we will rotate it by 180 degree. Then methyl, the upside methyl will come downside at the place of chlorine. The chlorine will go at the place of methyl, and then the other four substituents will also change their places. Like this hydrogen will now come to here and this chlorine will now come here. This methyl will go now here. So now you compare the two structures. The structure we will get by rotating this molecule by 180 degree will be exactly this same compound. So we are seeing that these two compounds are interconvertible by rotating one of these at an angle of 180 degree. Hence, these two compounds are identical. These are the same stereoisomers. So, if we look at the options now, we have option B is correct. Structures given 2 and 3 are the same stereoisomers. I hope the question is clear to you all. Option A, compound A we excluded because it was possessing two chlorine atoms. Even if we rotate this molecule also by 180 degree, that will not be identical as these two. So 2 and 3 are the same stereoisomers. Let's move to question number 6. One of the most important consequences of two compounds being atrope isomers of one another is that it results in dash molecules. So this is a very simple question. You just have to answer. Atrope isomerism results in two different molecules, and those two molecules have what kind of relationship? Will those molecules be non-chiral or chiral? or those two molecules will be isomers, or those two will be superimposable molecules. If we recall the principles of isomerism, this phenomenon can be best explained by considering a biphenyl molecule, okay, which will have substituents at the ortho positions, and the substituents in one ring must be different. So we have a biphenyl molecule here, and the planar conformation of this biphenyl ring is highly statically crowded due to the presence of substituents at the ortho positions in both the rings. Okay, they cannot be placed in a planar conformation because the ortho position substituents will have high statical crowding. Because of this, along this axis, these two rings cannot undergo rotation. As we know that hydrocarbons undergo rotation at room temperature because of like they can undergo free rotation at room temperature itself along the axis. But for this biphenyl ring, along this axis, there can have no free rotation due to the presence of ortho substituents, and in such cases these type of molecules show isomerism, and such type of molecules results in non-superimposable mirror images. Thus, if we go back to our options, isomerism in molecules results in chiral molecules. Like for example, we have this biphenyl compound given. If we had iodine on this side and bromine on this side, that molecule would be an isomer of this given molecule, okay, and both of these two will be chiral molecules. The next question is also from the same topic, isomerism. What type of strain is hindering the two compounds below from freely rotating and interconverting between one another? So why, I have already explained in the previous question, why can these two phenyl rings connected by one axis not move freely or cannot rotate freely? Is it because of diaxial strain? Is it because of torsional strain? Is it because of steric strain? Or is it because of molecular strain? We have already discussed that when these two phenyl rings of a biphenyl system contain different substituents at the ortho positions, there will be very high amount of steric crowding, due to which they will not be able to move freely and they will not be able to convert into one another. So the answer will be option 3, steric strain. Then we have the next question. Question number 8. Label each asymmetric carbon in the compound below as R or S. You have to do two things. First, you have to identify all the asymmetric carbons present. Second, you have to assign the R or S configuration to all the asymmetric carbons present. So if we look at this molecule, we have only one chiral center or asymmetric center because this carbon is attached to 4 different substituents. So now we have to assign the configuration. What will be the which substituent will be given the first priority? Following the atomic number rules, this will be given the first priority, isn't it? This is oxygen, so this will be of the first priority, and then this substituent will be of second priority, because we can simplify this alkene by writing this carbon atom attached to two carbon atoms and one hydrogen. So this will be of second priority. This alkyl chain will be the third priority. And at last, this methyl group, which is below the plane, that is away from us, will be of fourth priority. Okay. So if we move from 1 to 3, 1, 2, 3, we are moving in this direction. Okay. That is, we are moving in an anti-clockwise fashion. Thus, this center has an S configuration. Okay. Remember, this has been assigned as S configuration. In question 9, label each asymmetric carbon in the compound below as R or S. We have to first identify that this molecule has how many asymmetric carbon atoms, and then we will assign the configurations to the asymmetric carbons. But since in this Newman projection it is a little difficult to visualize, you can simply convert it to first Sawhorse projection and then convert it to Fisher projection, just like we did in the earlier example. So if we convert from Newman to Sawhorse, just lift the molecule in place and look at it from a different angle. You will see that hydroxyl will be above for the center, and the below the backside carbon hydroxyl is below side. And then you just have to simply place the substituents present at each asymmetric carbon. Hence, we have two asymmetric carbon centers present for this molecule. Okay. Now, just like we did in the earlier case, we will convert it to Fisher projection. For that, you have to bring those substituents in the same direction which are present in the same plane. See, this hydroxyl and this hydroxyl are present in the same plane. So, you have to rotate it by 180 degree so that this hydroxyl will come above. So, by rotating it by 180 degree, this hydroxyl and this hydroxyl becomes parallel. It comes here, and let us look at the hydrogen and methyl now. This hydrogen on rotating by 180 degree comes here, and this methyl on rotating will come here. Okay, this methyl becomes parallel to this hydrogen. This hydrogen becomes parallel to this methyl, and now we have to lift that parallel Sawhorse projection to the Fisher projection, and you will get these two hydroxyl at the axial positions and the parallel substituents in this way. Okay, this OH came here, this hydrogen came here, and this methyl came here. Thus, you have this Fisher projection for this compound, and now we will assign the configuration to the asymmetric carbons present. And I hope you remember the rules of assigning configurations when it comes to Fisher projections. Okay, when the fourth priority group is present in this axial position, we will simply follow the clockwise anti-clockwise rule similar to RS. Like if it is going clockwise, then it will be R configuration, and anti-clockwise will be S configuration. But in case the fourth priority group is present in the horizontal planes, not in the vertical, then you have to reverse the rule. Okay, like if the fourth priority group is present in this horizontal plane, the clockwise will be S, not R, and the anti-clockwise will be R, not S. When the fourth priority group lies in the horizontal plane, the rules reverse. So now let us assign it for this compound. For this center, we have this one as first priority group, the OH one, and this alkyl chain, whatever is rest here, okay, this will be the second priority, this methyl will be third priority, and this hydrogen will be the fourth priority. 1, 2, 3, 4. Let's move from 1 to 3. 1, 2, 3. 1, 2, 3. We are moving in an anti-clockwise direction. But the fourth priority group is placed in the horizontal plane. So like I said, the rules will reverse. So anti-clockwise becomes R. Okay, I hope this is clear. The hydrogen is placed in the horizontal plane. So the rules will reverse and the anti-clockwise becomes R. Similarly, let's look for the second center. This is 1. This is 2. This is 3. And this is the fourth priority group. And similarly, here also the fourth priority group lies in the horizontal plane. Hence, the rule will reverse in this case also. So, if we move from 1, 2, 3 in an anti-clockwise fashion, according to the rule, anti-clockwise will be R. Hence, this molecule will have two asymmetric carbon atoms having RR configuration. I hope this answer is clear to everybody. How we assigned these two centers as R and R. So next we have question number 10. How many stereoisomers of 2,3-butanediol exist? You are given the formula of 2,3-butanediol. You have to identify how many stereogenic centers, stereoisomers of 2,3-butanediol are possible. The answer will have to be solved in the similar way like we did for question number 3 in the case of tartaric acid. Okay. First, let us write the Fisher projection of the molecule given 2,3-butanediol. We can write 4 different stereoisomers following the rule 2 to the power n. And since the molecule possesses 2 stereogenic centers here, so 2 to the power 2, that is 2 square, will be 4. So 4 different stereoisomers you can draw. But you will see that structures C and D are interconvertible by when we rotate one of this by 180 degree. Because if you rotate this molecule through this axis passing vertically, you will get the same compound as D. So C and D are identical. They are superimposable mirror image and they will be identical molecule. Hence, only 3 distinguishable stereoisomers are present for the molecule 2,3-butanediol. Next, we have question number 11. Cis-2-butane on reaction with bromine gives 2,3-dibromobutane, which is dextroisomer, mesoisomer, racemic mixture, or levoisomer. When cis-2-butene is subjected to reaction with bromine, Br2, you get 2,3-dibromobutane, but you have to identify the product. Is it chiral or is it meso compound? That is, it has stereogenic center, but it is not chiral due to presence of plane of symmetry, etc., etc., or it will give a racemic mixture of two kinds of products, two or more kinds of products. You have to identify that in this question. So when you subject cis-2-butene to react with bromine in presence of some solvent, you get basically two different types of product. Okay, how? If we follow the mechanism of the reaction for the reaction of cis-2-butene with bromine, first the double bond will attack at bromine by knocking out this bromide ion, and in return you get this bromonium ion, where both the carbon are connected to one bromine atom, and this bromonium ion intermediate you get in the first step of this reaction. In the next step, the bromide ion which was knocked out in the first step will come back into the picture, and it will attack at the bromonium ion. That is, this bromide ion in the second step will attack the bromonium ion either from this side or from this side. If this bromide ion attack it from this side, then bromonium ion will open up in this way, and we will have bromine here, and this bromine will be here in the opposite direction. This bromide comes here, this bromonium ion opens up, and this bromide in return comes here. That is one case when bromide attacks at this center. What if this bromide attacks here? It will attack here. You will get bromine here, and bromonium ion will open from this side. This time, okay? So this time this bromine will go this side. Thus, you have these two types of different types of products possible by attacking the bromonium ion in two different positions. See, if the bromide ion attacks here, you get this product, and if the bromide ion attacks here, you get the second product. And you cannot selectively get one product in this reaction. So you end up getting a mixture of two products which are enantiomers of each other. These two products formed are enantiomers of each other. These two are non-superimposable mirror images of each other. See, suppose we are placing one mirror here, like in place of the AND word, we are placing one mirror. These two will be mirror images. But if you lift this molecule and try to place it above this molecule, the two molecules will be mirror images but not superimposable. Thus, you get a mixture of two enantiomers, which is called a racemic mixture. So, the answer to this question number 11, cis-2-butene on reaction with bromine gives 2,3-dibromobutene, which is a racemic mixture. Thus, option C is the correct answer for question number 11. Then you have question number 12. How many asymmetric carbons are present in the compound below? You are given the chair conformation of this pyrene ring. Okay, the 6-membered hydrocarbon having one oxygen atom as a member of the 6-membered ring. This pyrene ring contains substituents at all the carbon atoms which are member of the 6-membered ring, and you have to count the number of asymmetric carbons present in the compound. Okay, let us count the asymmetric carbon number. This is one carbon center. Is it connected to 4 different substituents? Yes. 1, 2, 3, and fourth will be one axial hydrogen. So yes, this is an asymmetric carbon atom. Next up we have this carbon atom. Is it connected to 4 different substituents? Yes. Hydroxyl. Then this is another substituent. Then this is the third substituent, and one axial hydrogen which is not shown here is present here. Okay, thus it has 4 different substituents. Then you have this third carbon atom where it is connected to one hydroxyl, one alkyl chain, one different alkyl chain, and then there will be one axial hydrogen. Okay, so yes, this is also another asymmetric carbon. Then this is the fourth carbon atom. This is also connected to 4 different substituents, one hydroxyl, one alkyl chain, a different alkyl chain, and then one axial hydrogen will be present here. And the last carbon atom of the pyran ring is connected to one ether linkage in this way, one CH2OH group in this way, one alkyl chain in this way, and one axial hydrogen will be present here. So this carbon atom is also asymmetric. Okay. So the answer of this question number 12 will be number of asymmetric carbons present in this compound will be 5. Okay, 1, 2, 3, 4, 5. All the 5 carbon atoms which are the members of the pyran ring possess 4 different substituents, and those will be asymmetric carbons. In question 13, how many asymmetric carbons are present in the compound below? Again, you are given this tartaric acid. We have already solved a question on the tartaric acid, and we came to know that this compound has 2 asymmetric carbons present, and both the 2 asymmetric carbon centers will possess one carboxylic group, one hydroxyl group, one alkyl chain, and one hydrogen atom. So the answers to question number 12 and question number 13 will be 5 and 2 respectively. Hope these questions are clear. Then you have question number 14. Which of the following terms best describes the pair of compounds shown? Are these enantiomers, diastereomers, or the same compound? You are given a pair of molecules, and both the molecules contain an asymmetric carbon atom which is connected to one methyl, one carboxyl, one amine, and one hydrogen atom. Okay, both the compounds contain the similar substituents, but we have to identify, are these substituents placed in the same orientation or in a different orientation? And if we notice the orientations, will these compounds be the same compound, or will these be mirror images? And if they are mirror images, then will those be superimposable or not? So for that, let us try to assign the configuration to both the compounds. Okay. For the first compound, we have the priority groups assigned in this fashion. This will be nitrogen has higher atomic number than carbon and hydrogen, so this will be definitely the first priority group. So first priority group is arranged in above the plane towards us. So here we have written the number, okay, 1. Then carboxylic group is the second priority group. Hence, we have placed it here, 2. Then methyl is the third priority group, 3. And hydrogen is the fourth priority group. So, we have 1, 2, 3, 4. But to give the configuration, to assign the configuration, we need the fourth priority group either above or below the plane. We cannot have the fourth priority group on the plane of paper. Otherwise, we may make a mistake while assigning the configuration. Okay, so you must bring the fourth priority group either above the plane or below the plane, so that we can easily assign and correctly assign its configuration, whether is it R or S. So for that, we have a rule. You have to exchange the pairs of substituents present. Okay, I will show you. See, let us consider these two, 1 and 4 as a pair and 2 and 3 as a pair. Now we will exchange their positions. 1 and 4 will be exchanged and 2 and 3 will be exchanged. Okay, so if we exchange, we will have 4 here and 1 here, 3 here and 2 here. But remember, if you are exchanging, you have to exchange both the pairs of numbers. You cannot exchange only one pair and then leave 2 and 3 in the same position. Okay, you have to exchange both the pairs of numbers. Thus, if we exchange this pair and this pair, we will get 2, 3 here and 1, 4 here. And don't think that after exchanging both the pairs, will the compound remain same or it will be different? It will be the same compound. Okay, it will always be the same compound. We are just arranging the same structure, the same molecule in space, so that we can correctly assign the RS nomenclature here. So we are ended up here where we have 1, 2, 3, 4 substituents like this fashion. Okay, now we will move from 1 to 3 so that we can assign 1, 2, 3. We are moving in a clockwise direction. 1, 2, 3. We are moving in a clockwise direction, but look at the fourth substituent. It is above the plane or below the plane? It is above the plane. Okay, so when if we recall the rules of RS nomenclature, if the fourth priority substituent is above the plane towards you, then you have to reverse the clockwise anti-clockwise rule. If the fourth substituent were below the plane, we could have simply say that clockwise will be R, anti-clockwise will be S. But since the fourth priority substituent is above the plane, this time you have to reverse the rule. So 1, 2, 3, although you are getting it as R, you have to end up saying it as S. Okay, so this compound will be having S configuration. This molecule will have S configuration. Okay, then we have the next molecule, and we are left with, like, we have to assign the configuration to this center now. You have already seen that it is S, but let us try to solve it and verify it. Is it R or S? Okay, so this is the first priority group here. This is the second priority group here. This is the third priority group here, and this is the fourth priority group here. And you can see that in this Fisher projection, the fourth priority group is placed in the horizontal plane. Okay, so if we move in a clockwise direction, that configuration will be S, and the anti-clockwise direction will be R, because the fourth priority group is placed in the horizontal plane. So if we move from 1 to 3, 1, 2, 3. 1, 2, 3. We are moving in a clockwise direction for the compound which contains the fourth priority group in the horizontal plane, and we have to assign the molecule as this will be COOH. Okay, this is carboxylic group. So we have to assign it as S configuration. Hence, you see that both the centers, the stereogenic centers of the molecules have an S configuration. So the compounds will be identical, or they will be the same compound. Okay. If we had found that one of these was S and the other would have been R, then we would have called it as enantiomer. Next, we have been given various pairs of molecules where you have to indicate the relationship between each of the compound pairs given. Are they enantiomers? Are they diastereomers? Are they constitutional isomers or identical compounds? So for that, you have to recall all the rules of assigning stereochemistry to the stereogenic centers in case of like how we have solved the questions today on Newman projection, on Fisher projection, and or Sohor's projection, and then you will be able to solve all these questions. I have also attached the answers to all the pairs. To solve the first pair, to solve the first pair, you have to convert both the molecules given in the first pair into their Fisher projections. And after converting the molecules into their Fisher projection, you have to assign the stereochemistry like RS configuration to the asymmetric carbon atoms present. Okay. So we have already solved similar kind of examples, and I hope those solutions will help you in solving this question for these two pairs, and you will find that these two pairs will be diastereomers. Okay, you just have to convert it into their Fisher projections and you will find the configurations which will lead to the verification that these two compounds are diastereomers. Similarly, if you try to solve for this pair, you have to convert these two molecules into their Fisher projections, and you will find that the stereogenic centers present in both the molecules will be of same configuration, and you will see that these two molecules will be identical. So for these two pairs you can solve by yourself. Okay, for these two you can see that these two molecules are one is given cis, like the higher priority groups are oriented in the same direction, and for this molecule the higher priority groups, like this will be 1 and the hydrogen present will be 2, and for this will be 1 and the hydrogen will be 2. So 1 and 1, the higher priority groups are oriented in the opposite direction, hence it has a trans fashion. So this cis and trans geometric molecules will be diastereomers. Okay, they are not mirror images of each other. For the next pair, you have two cyclobutane rings, and both the cyclobutane rings contain two chlorine substituents in the 1,4 positions, 1,3 positions. Okay, in both the molecules you see in 1,3 positions you have chlorine substituents, but if you look at the two molecules, they are definitely not identical, because for this chlorine substituents they are oriented in different directions. This chlorine atom is above the plane and this chlorine atom is below the plane, and also these two molecules are not mirror images. Although they have the same molecular formula, they are not mirror images. Forget about superimposable, non-superimposable. They are not even mirror images. Hence, according to definition, you have to term this pair as a pair of diastereomers. Similarly, if we try to solve for this pair, you are given two pentane molecules and you have one chlorine substituent in these two molecules, okay, in each of these molecules. If we try to visualize, you will know that these two molecules are mirror images of each other. Like, imagine placing a mirror above this molecule and then placing the second molecule above that mirror, that is above the plane. You will find that these two will be mirror images. You can also verify the mirror image relationship by assigning the configuration to the asymmetric carbon atom. Like, for example, for this one, we have this one as the highest priority, this one as second priority, the methyl as third priority, and the hydrogen present, which is below the plane, will be fourth priority. And if we move from 1 to 3, 1, 2, 3, you are moving in an anti-clockwise fashion where the fourth priority substituent is below the plane, then you have an S configuration for the center. Similarly, for this one, you have this as 1, this as 2, and this as 3, and the fourth priority group is above the plane, like towards us. So the anti-clockwise rule will reverse. So 1, 2, 3, although we are moving in anti-clockwise fashion, we have the fourth priority substituent above the plane, and we will end up getting R configuration. So we have one S and one R for this pair, and these two will be enantiomers of each other. Okay. Similarly, for this pair also, you are given the cyclohexane conformations of these two compounds. You have to simply convert them to the planar geometry of the cyclohexane and place the substituents according to above or below. Like, for example, this equatorial methyl is above the plane of the cyclohexane. Okay, so it will be above the plane in the planar structure, and this axial hydroxyl will come below the plane. Hence, you have to convert both the molecules given in the pair to their planar geometries, and you will find that these two compounds are mirror images of each other, but they are non-superimposable. Okay? Like, for example, if you place a mirror between them, then you will find, like, for example, we are placing a mirror above this molecule, okay, above the plane, and then we place this molecule above the mirror. You will find that these two are mirror images, but they will be non-superimposable. Hence, you will get a pair of enantiomers. Next, we have this pair where you have another pair of cyclobutane rings having all the carbons possessing one methyl substituent. But here you have these three above the plane, this one is below the plane, and here these three are above the plane, this one is below the plane. But do you remember the rule? If we are comparing a pair and we take one molecule of the pair and rotate it by 180 degree, if it becomes converted into the second molecule, then those two will be identical. Okay. So we have to rotate one of the molecules by 180 degree. Let's hold this methyl substituent and rotate it in 180 degree. This methyl will come here and this below the plane methyl will come here. And we get what? The isomer where we have rotated it by 180 degree, which is the similar compound as the second molecule of the pair. Hence, they have a C2 symmetry relation, that is 180 degree rotational axis relation, and they will be called identical. For this pair of molecules, you have to simply assign the RS configurations to all the stereogenic centers present in a molecule. Like for example, in this molecule, you have two stereogenic centers. Following the rules, whatever we have revised in the earlier questions, you just have to assign the RS configuration to these two stereogenic centers, and here also you have to assign the stereogenic centers RS configuration, and then you will find that this pair is a diastereomer. Let us solve this question, and then you try to solve this question by yourself, the way we are going to solve this one. Okay, for this pair you have two stereogenic center for this molecule. This will be the first priority group, this will be the second priority group, and this will be the third priority group. So on moving from 1 to 3, 1 2 3, we are moving in a clockwise direction, but the fourth priority group is in the horizontal plane, so we will have this one as S configuration. 1 2 3. We have the center is S, and for this center 1 2 3. For this center it will be R. S R. Remember, okay, we have gotten SR for the first molecule. For the second molecule, we have 1 2 3. Clockwise direction, but fourth priority is in horizontal, so it will be S. 1 2 3 S. And for the second center, 1 2 3, like this. Okay, so you have 1 2 3, you have S configuration. Thus we have SS configurations for the stereogenic centers present in this molecule. Earlier one have SR and this one has SS, then SR and SS will not be mirror images of each other, and they will be diastereomeric compounds. So this pair we found that having SR and SS configurations, these two will be diastereomers of each other. So I'm asking you all to solve this pair in the similar way. You just have to assign the RS configurations to the stereogenic centers present in both the molecules, and then you will find that these two molecules in the pair will be enantiomers. Okay. Similarly, for these two molecules, if you try to solve, you have to assign the stereochemistry for the asymmetric carbon atoms present. Both the molecules have asymmetric carbon atoms present, two asymmetric carbons present, and if you assign the RS configuration to both the centers in each molecule, you will find that these two molecules will be diastereomers of each other. Even if you do the visualization by placing a mirror in between these two molecules, you will see that these two are not mirror images of each other, because this chlorine for this molecule is above the plane, but this chlorine for this molecule is below the plane. So if we place a mirror here in place of the word diastereomers, if we place a mirror here, these two will not be mirror images of each other. Okay, so you will find that these two molecules are diastereomers of each other. Hence, we have solved these questions on the topics stereochemistry, and let us quickly go through the questions that we have discussed today. First, we saw this question where you had to identify that the given pair of molecules are enantiomers, diastereomers, or they are the same compound. And for that, we assigned the asymmetric carbons present in both the molecules, whether they are R or S, and we found that these two molecules were having RR and SS configurations, and hence they were termed as enantiomers. In question 2, we learned how we name this kind of compounds which are possessing axial chirality. We placed our eyes here and we tried to visualize the molecules in accordance with their substituents present in the horizontal plane and in the vertical plane, and we found that compound B and C were achiral compounds because they were having same kind of substituents in this vertical plane and here in this horizontal plane. So B and C were achiral. Compound A was chiral and it was having R configuration, and compound D was also chiral but it was having an S configuration. So we saw that answer A was correct. Then we solved the number of stereoisomers present for the tartaric acid molecule given, and we saw that although according to the 2 square formula we found that it must have 4 stereoisomers possible, 2 of the stereoisomers were the identical compounds, so we saw that the number of stereoisomers possible was option number C, that is 3. In question 4, we had to label each asymmetric carbon in the compound, and we saw that both the stereogenic centers present in this compound were having S configuration. In question 5, we had to identify the stereoisomers which were same. For that, we first converted all the Sawhorse configurations into their Fisher projections, and we saw that compound option B and option C, like compound B and compound C were the same stereoisomers, and compound A was different since it was containing 2 chlorine atoms on the same side. In question 6, we talked about atrope isomerism, where the most important consequences of 2 compounds being atrope isomers of one another is that it results in chiral molecules. And we saw that steric strain hinders these 2 compounds from freely rotating and interconverting between one another. It is the steric strain what is hindering. Then we tried to assign the asymmetric carbons present in the compounds given, whether these are R or S, and we saw that the question 8 molecule was having S configuration, and for the question number 9 the compound was having RR configuration. And then we moved to number of stereoisomers possible for 2,3-butane diol, and we solved this question in the similar way we did for question number 3, tartaric acid question, and we found that it has 3 non-identical stereoisomers possible. Then we discussed how cis-2-butane reacts with bromine. to give 2,3-dibromobutane, where in the reaction first we were getting a bromonium ion which was opened by bromide ion in two different way. Either it was attacking in this carbon or this carbon and giving us the mixture of two enantiomers, and thus the option C, racemic mixture, was the correct answer for this question. In the next question, we discussed number of asymmetric carbons present in this pyrene ring, and we saw that all the 5 carbon atoms of the pyrene ring were asymmetric. And question 13, we had how many asymmetric carbons present in this below compound, which is a tartaric acid, and we saw that this tartaric acid molecule has 2 asymmetric carbons present. In question 14, we had to describe the pair of compounds as whether these are enantiomers or diastereomers or these are the same compound. For that, we first assigned the asymmetric carbons present in the given molecules as R or S, and we found that both these molecules are having S configuration for the asymmetric carbon, and we termed them as the same compound. And then in question 15, we had multiple pairs of compounds and we had to identify them as enantiomers, diastereomers, or constitutional isomers or identical compounds. And I asked you to solve these two pairs by converting them to their Fisher projections and then assigning the RS configurations. And this question also I have asked you to work out the similar way we solved as this one, and thus we have arrived at the end of this week 3 tutorial. Okay, so thank you everyone for joining. Feel free to discuss any kind of queries or questions you had related to this week's tutorial, and I again